你上次是上完
对
这个，
对，我把它开了。Okay, last time we start here, okay, a bit about content-based message routing. And here we will discuss pop-sub system. Okay. In general, there are 4 different kind of operational mode. Okay, the reason for this is that because you can use different kind of interface, okay, to approach the similar functionality. The first one is the middleware acting like a notifier. Okay, so both publisher and consumer and subscriber, they use push mode or push interface. Okay, that means from the point of view of publisher, the push means publisher send message to the middleware. Okay, and the push mode for the subscriber means the middleware pushes the information to the subscriber. Okay, so that's so middleware play the role as a notifier. So something happens, publisher tell the middleware, and then middleware tell inform the subscriber. Okay, the second part is they both use pool operations, okay, or APIs. So the middleware act like a cloud or repository, okay, or cloud plus repository, okay, more specific. Okay, that means the middleware will actively cloud try to get the information from those publishers. Okay, so the publisher will not send the message to the middleware, but just create a message, but in its local disk or in its local server. Okay, and that's the responsibility of the middleware. Periodically or any by any means, like okay, the cloud, the middleware, they will get the information created by the publisher from their local storage and then store in middleware's repository. Okay, and also after that, the consumer or the subscriber, they also need to go to the repository provided by the middleware to retrieve the information they are interested. Okay, of course, how the middleware will know there's something new in the publisher disk or repository, or how the consumer will know there's some information, new information there, but they may be interested. That's another issue. Okay, in general, there's a notification mechanism. Okay, so for example, the publisher after they generate something, they just inform the middleware or maybe all the data they generate, you have a timestamp in there. So the middleware periodically they go to the storage of those publishers, and then they just retrieve those newly published data, okay, and so on. And after that, they will generate some notification information, just the control information to those interested subscriber. And then subscriber, after they receive this notification, they can decide when they want to retrieve those information from the middleware. So the middleware is like cloud plus repository. Okay. The third mode is that publisher use push mode. Okay, but consumer use pull mode. It's a hybrid between the push interface and pull interface. So the middleware will act in like a queue, a message queue. Okay, so whenever there's a new thing generated by publisher, they just send the message to the publisher, and the publisher store it. Okay, and then because the subscriber they need to be they use pull interface. That means the middleware will notify those subscribers, but just notification. Okay, they will not send the message out. They just send the notification to inform those subscribers there's something new you may be interested. So that's the subscriber's responsibility, and they can decide when they want to retrieve those information they may interested. Okay, so that's the third mode. Another hybrid mode is that publisher use pull interface, but subscriber they use push interface. Then the middleware is acting like an agent of the consumer, of the subscriber. Okay, they get the information from the publisher. Periodically, they try to find out there's some new information generated in the publisher side, and then after they retrieve the information, they send out the whole information to those subscribed consumers. Okay, so the subscriber they don't need to act on their own to get the retrieve information. They just see there. They will receive after subscription. They will receive those information they register. Okay, they subscribe by the middleware directly. Okay, so conceptually it's something like this. Okay, the push means the information flow will go from subscriber to middleware and then to the consumer by the push interface. Okay, this is the first model. Okay. And the second model is that they all use pull mode. So you can see the information flow in the reverse way. Okay, so consumer subscribe, and then the event channel or the middleware they get the information from the subscriber and then store in its repository. And then it may generate information and notification to notify those consumers. They can decide when to retrieve those information by using this pull interface. The hybrid mode is something like this. Okay, this first one is a queue. So the supplier or the publisher, after they generate new info, they just send to the middleware directly. Okay. And the middleware inform the consumer. Consumer decide they retrieve this information from the queue. Okay, and that's what is in the reverse order. Okay, the event channel or the middleware they cloud for the new information. After that, they send out the information to the consumer directly. So this four kind of operational mode, they all achieve the same functionality of pub/sub mechanism. Okay, but by different ways, okay, different approaches. But depends on how the middleware implement their functionality. But most of the time, most of the middleware or pub/sub middleware currently they may support not all these four models, but in general they will support one or two operational models, the interfaces. Okay, depends on what kind of implementation they use. Okay, so that will conclude this lecture about distributed systems. The message passing. The next lecture is we were talking about inter-process communication facility, specifically the message passing mechanisms. Okay? To share information among processes, okay, in general, we require some kind of communication facility between these processes. And this mechanism usually called inter-process communication facility, or abbreviated by as IPC. Okay, and in general, there are two kinds of IPC mechanism. One is message passing approach. Okay, the shared information is physically copied from address space of one party to another party. Okay, it's like you copy the information from address space of sender to the address space of the receiver. Okay, and the second approach is shared memory approach. Okay, in this approach, the sender and receiver, or these communication parties, they may have a shared common memory area. Okay, shared memory. And so they can use the read-write operation, or just normal update, store and load operation to change the content of this shared memory area. So the other party will see the updates, okay, and they get the information they would like to change. Okay, so this is another approach. Okay, and here we discuss the message passing facility. Okay, so in the message passing IPC, okay, in general, we first need to define what is a message. Okay, a message is a collection of data, object, and some structure, related structure. So in general, a message consists of a fixed length header, okay, which contains some information. In general, this information may contain the address of the senders and the address of the receivers, or other attributes that are needed for this message routing. Okay, and they may contain fixed length or variable length message bodies. That's the actual data they want to transfer, okay, or exchange. And this message body may including a collection of typed data objects. Okay, so that's the general definition of the message. Okay. For fixed length message body, okay, if a message contains fixed length message body, that means the overall the size will be fixed. Then the management effort or the communication system to manage this message will be much simpler. Okay, because then every system, every host, they can just use a pool of fixed size buffer to store those messages. Okay, so the processing message and the management of these buffers become straightforward, because you can use a sequence of array elements, okay, for these buffers. However, if the message body is variable length, then the management become much complex. Okay, so in general, we need to have a dynamic memory allocation mechanism. For example, use a heap. So dynamically, because every message you anticipate maybe have different size. Okay, so you need to dynamically allocate those buffers. So in general, you cannot just use a sequential array for this. A heap will be the most common way for that. Okay, and because the size is different, okay, so some kind of garbage collection mechanism may be needed. Otherwise, because of the size is different, so we all know from the operating system, or if it use dynamic allocation mechanism, then it's possible you generate a lot of fragmentation. Okay, so garbage collection means you need to do some compact memory compaction to restore those memories become much easier to use, and so on. Okay, so and these mechanisms are usually much complex than this straightforward sequential arrays. Okay, so that's the difference. Okay. That's why most message passing systems, okay, they prefer this fixed length message packets. Okay, for handling messages. And the communication between sender and receivers, in general, we can have two kind of communication model. One is we call it direct communication model. Okay, and in the term this direct communication model usually means that the process, the sender and receiver, they need to specify during the communication. They need to know their counterparts in advance. Okay, for example, the sender needs to know who is its receiver. Okay, before you can send the information. Okay, and usually they require a global naming mechanism or global ID mechanism. Okay, for this kind of communication model. So sender can specify the ID of the receiver, and the receiver may sometimes need to specify the ID of the senders. Okay, and for this direct communication model, we can also usually the system may support two kind of APIs. One is the symmetric addressing API. That means both sender and receiver, they need to explicitly identify their counterparts, okay, in this operation, input these operations. Okay. For example, their API may look like this. When you try to send information, you need to specify the destination and also define your message. So both message and the destination address are input arguments. Okay, here ins means they are input arguments. Okay, and in the receiver side, okay, they need to specify where the message should come. Okay, so they need to specify the source address. But because it is a receiver, so they need to declare a return buffer. Okay, so the message will be an output argument. So after this receive return, this message will contain the arrived message. Okay, so here the interface will be something like this. Okay, and for the second kind of mechanism, we call it asymmetric addressing. That means only the sender need to specify the receiver. The receiver, they can use both the source address and message output argument. They can define. That means any sender, as long as their message is designated to this particular receiver, the receiver are willing to accept. Okay. So for this kind of interface, the receiver can specify both source address and the message can be specified as an output argument. Okay, that means you don't need to give a particular source address. You just allocate the buffer space in there. Okay, so after this receive operation return, both this source address buffer will contain the real source address of this particular message, and this message buffer will contain the arrived message itself. Okay, so in general, this direct communication model we will have these two kind of interfaces. Depends on the underlying mechanism. They can support this or this or support both. Okay, because the sender API for send will be the same. Only the receive can be different. So some systems they can support both. Okay, so the receiver can decide if they don't care about which sender, as long as the message is designated to the receiver, then they would like to receive. Okay, because some application there's no strict relationship, because multiple sender may try to contact the same receiver, right? So from the receiver's point of view, the order of this message to handle this received message, they may be irrelevant. Okay, so they can just use this asymmetric address to receive any message. Okay, they can okay, right, and then process those messages in the real received order instead of specify for each message define this one should came from one particular sender and so on. Okay, so depends on application requirement. Okay, both addressing mode can be used. Okay. The advantage for this one is simple, because the communication is very straightforward. Okay, and the mechanism is very easy. The semantic is easy to understand. Okay. The disadvantage is that this naming mechanism they require if the process, the name of a process or the ID process been changed, then all the related program then may need to be changed also. Okay, and also because this naming mechanism, the sender, at least sender need to know the address of the receiver in advance. Otherwise, the communication system cannot be able to deliver the message. Okay, so that's the major disadvantage of this kind of model, communication model. Okay. So in this kind of communication, the major or critical issue is that how to name a particular address process in this distributed system or in this system which contains multiple hosts. Okay, so in general there are three kind of common ways. Okay. The first one is every process use a host name plus its local ID. Depends on where this process was created. Then the ID will be assigned by its local host, local operator, and we put a host name in front of this ID. Then this will be globally unique. Okay. So you can use this name. Okay. The second possible way is that instead of two elements, we use three attributes. The original host name, that means the process was created by this particular host, and with the local ID assigned by this particular host, plus a host name. That's because during the life cycle of the process may be moving around or migrate from one process or one host to another host. Okay, in the distributed system, it's possible. Okay, so to cope with this situation, so we use this second host name. The second host name usually is the host that currently running this particular process. Okay, of course, because the process can be moving around during its life cycle, so this name can be maybe dynamically changed. So to resolve, to find out a process's name in general, okay, we use this tool with the base knowledge or the current knowledge of this host name, okay, as the address, global ID, and try to send message to there. Okay. So initially, this second host name and the first host name will be the same because when the process was first created, its creator and its current host will be the same. Okay, so and when the process migrates to a new host, then the second host name will change to become the new host. However, this change, you don't need to broadcast it. You don't need to tell everyone. Okay, only every host maintain a table to record if there's a process is moving from this A host to another host. Then you make a record about this migration. Okay. So when a host receives a request to a particular process, this process, the second host name is itself, right? So the other party, other host, they think the process is still there. But anyway, if the process is still in this host, then you just deliver to that process. If the process is already has been moved to others, then your mapping table will contain this information. So you just forward this message to that migrated host. Okay, and this forwarding can be continued because when you forward the request to that particular host, the process may move to others as well. But in any way, that host should have this, we call this migration information. So the host can always forward this request. Eventually, this forwarding request message will arrive to the real new host, okay, the current host of this particular process. Then the process will receive the message. Okay, and when you receive a message, after processing the message, generate a response. Then either the response will can contain the new name of this particular process, okay, and piggyback to the sender. So then sender will know, okay, this process now is running in this particular host. Okay. Also, next time when the sender try to send message to that one, the person may already be moving to others. But anyway, as long as every host maintain this migration information, then it's always possible to find out, to forward the message to the real host, which contain the receiver, okay, and so on. Okay, so that's the mechanism for this. Okay. There's a host name plus ID, local ID plus host name. The third way is that you create a global name server to map a process, the human readable string name to its current global ID. Okay, and the current global name maybe use this host name. Then here the host name is the current host. Okay, with local ID. So we use a global name server to maintain this mapping. Okay. So then whenever you move a process from one place to another, you change the global name server, change the record in this global name server. Okay. And so before any sender trying to send to a process, send a message to a process, they look at this global name server. Okay. Use. So now the address will be, the real address will be something like this, okay, real address. But in the send and receive APIs, the destination address or the source address can be used, this human readable string names. So you don't need to remember those ID based names. You just use human readable name. then it's possible these human readable names can be created uniquely, okay, and so on. So that's the most common way for name globally identify a particular process for these direct communication models. Okay, because this in long term to maintain this is not, of course, the mechanism there, but make it very efficient, or it's not as simple as it looks. Okay, because you have an issue. How long this migration information should need to be kept in each host? You don't know, right? But if you delete any of these records, then the message may not be able to forward to the process. Okay. So the problem for this is that the most safe way is you keep there, right? Until what? Until the process terminates. Then the last host, after it terminates, you need to inform all the hosts this particular process is terminated. So any record relating to this process, you can delete it, can remove those resources associated to maintain the particular process. Okay. So you need to have something like this, okay, to make sure those resources associated with this record can be reused. Yeah. Okay, but and this kind of information will generate a lot of traffic, because you will see that a lot of process, when a lot of process is run in a typical size of the system, okay, they may have 1,000 computer nodes, right? So every node will maintain this table, and in any given times, they may have a lot of 10,000 or even million of process in the system, right? Okay. So to maintain this information, and when the process terminates, the process, the host need to inform all the hosts this particular process is terminated. Otherwise, the memory usage may become, you may have some garbage in there. Okay, and so the performance of the system may be downgraded. Okay, so most of the modern operating systems, they all have this kind of problem. Okay, so especially for the PC systems, when you run your host, and after a while the system becomes slower. Okay, if you don't clear or you reset, okay, that's the reason. The major reason is something like this: the garbage collection is not doing well, so you have a lot of system memory buffer was wasted, okay, in some places. So the system memory usage become too high. So eventually the performance will be affected, and so things. So that's the major problem for this kind of direct communication models. That's why we have indirect communication models. Okay. So in indirect communication model, they don't need to specify or know the counterparts in advance. Okay. So and they still can be able to exchange information. Okay. The typical way is that there's a shared data structure, or we call it mediating data structure. Okay, it's used among these sender and receivers. Okay, so instead of sender and receiver, they need to know each other in advance. They just need to know this shared data structure, and the shared data can be a file, that can be others. Okay, as long as you have a common knowledge about this shared data structure, and then use this shared data as middle elements, parties, to indirectly make this message passage become possible. So messages are sent to this shared data by sender, and then data can be retrieved from the shared data by receivers. So most of this indirect they may exist as a mailbox, or in internet protocol they use the transport pole, okay, or some system they use message queues. These are all these shared data structures. Okay. So the primitive for this in general they will have a create, open, close, destroy a mailbox. So we can create something. A mailbox. Okay. Here we use mailbox as an example. Port or message queue is similar, right? Okay. So we create this shared data structure, or destroy or open. Okay. And the creator and the user of this shared data structure can be different. Okay. For example, a mailbox may be created by system users. Okay, and used for those application users to use, but that's one possible, because this requires system resource. Okay, as in there shared data structure, you need to have a memory or file or whatever. You need to have a storage to associate with this shared data structure. So you can keep messages. Okay, when the send message, you kept there, and then later be retrieved by the receiver. That's all. And the API for the send will be something like you specify the mailbox as an input argument and message also. And the receiver they use this specify mailbox as input argument and the message as output argument. Okay. So in this way, the sender and receivers, they don't need to know each other. They only need to know this common data structure they would like to use. Okay. So in some sense, they are decoupled. Okay, because they don't need to know. Okay. As long as this mailbox or this data structure is existing there. Okay. And in the temporal and spatial relationship between the sender and receiver, they can be all decoupled. Okay, depends on the life cycle of this mailbox. Okay, some system may maintain this mailbox as persistent data structure. Persistent means there's no time limit. Okay, once it created, and then it always existed until it will be destroyed explicitly. Otherwise, it's always there. Okay, and for this kind of mailbox, then the sender and receiver, they are not only decoupled in temporal, they also decoupled in spatial also. Okay, because they don't need to exist in the same timeline. Okay, the sender can just put something in, and then they continue to do other things, or maybe exist terminated. And receiver later they can be retrieve information from this mailbox. It's still possible. Okay. So for either direct communication or indirect communication, okay, we all have this property of persistent or transient. Okay, it depends on the life cycle of the messages. Okay, if a message is transient, that means when the party involved in this communication terminated, then the message will be discarded. Okay. If a message we say it is persistent, that means the communication system have a buffer, can keep this message. So the parties involved in this communication, even they terminated, the message may be still there. Okay, so that's basically the difference. Okay? So in persistent messages are stored as long as it's necessary. So you need to explicitly remove the message from the communication system. Okay, so but in general, if the system support indirect communication model, for example, they have a mailbox, okay, like email. Usually, it's a typical example of this indirect communication model. Okay, everyone has an email address, right? And instead of you send to the user by its process, you send to a user by its email address. Okay, and this email address is, of course, the email address you need to know in advance, but the email address and the email client, each time you run an email receiver, you don't need to know the process ID of the particular email receiver. Okay, the instance, as long as the email address is there, then so email system is like a mailbox. Okay, the sender and receiver, they all recognize the same mailbox. Okay, and here the mailbox is the receiver's email address. Okay. So this mailbox is this kind of mailbox is a persistent, because the receiver, you don't need to always run your receiving client. Okay, but the corresponding mailbox is always there, right? Okay, so that's the. So sender can terminate after executing the send primitive. Receiver may retrieve whenever it needed. Okay, and these two, they don't need to exist in the same time instance, or even in same space. Okay. So, in transient messaging, it is only sender and receiver are running. Okay. That means if any party is terminated, then the message will be discarded. And also, the transient message usually will be discarded automatically by the communication system when they find out it cannot be delivered because one party is already out. Okay, and so the communication error or some other error message will be generated. The UDP and TCP, this transport protocol, they are both transient. Okay, so before you can try to communicate, both parties need to be there. Okay, you cannot use an UDP to send to a process which is not there. And TCP as well. Okay, because so in general, only this indirect communication system can implement persistent messaging. Okay. For direct communication system, it's very difficult to support persistent messaging. Okay. We're talking about this broken and non-broken sense, okay, before, okay, but here we will give more detail about how to implement and how to support this semantics. Okay, the broken and non-broken primitive, that means broken set, that means model usually means that the sender is blocked until either one of these happens. Okay, and which one, that depends on the underlying communication system. The implementation dependent. Okay, either the communication notify the acceptance of message, that means the message already being sent to the receiver side, then they can notify. You block, you send or return. Okay, or because if all the messages been delivered to the receiver, these two has little bit different. Okay, the acceptance of the message means is in the receiving process. Okay, in here the receiver usually means only the host. Okay, the receiving side. Okay, as long as the message came to the host of the receiving process, then from the sender's point of view, that will be okay, because that depends on the implementation. Okay, some systems the receiver they have a buffer, so once it kept in receiver host's buffer, then it becomes okay. Okay, or the message get a response. Okay, so not only send Okay, and maybe yes, okay. This one is in the host, this one is in the process level, and this one is after general response. Okay, so the table is something like this. Okay, this one is when the message arrive in the host, and this one is the message is delivered to the process, and this one is not only delivered to the process has processing the message and also generate the response. Okay, and the response comes back. So it depends on the semantic real implementation. Okay. If the system support this, that means receiver has a buffer there. The receiver host has support buffer. If in this, that means receiver they don't have a system buffer, but the receiving process have a buffer. They can store this incoming message in the receiving process address space. Okay, but before it handle, and this one is after handling. It depends on the semantics. Okay, or timeout. Okay, timeout means for any this timeout is the final exception. Okay, so because the machine close the machine boundary, so it's possible to get lost or other effects. Eventually, the machine is not delivered or for any reason. Okay, so you always require a timeout mechanism for this. Okay, communication, machine passing facility. Okay, so sender can be blocked until this fourth situation, and the receiver block. Blocking receive means the receiver will be blocked until the desired message is actually received or timeout again. Okay, because the sender may not send out a message or the message get lost or whatever. So eventually the receiver can set a timer. So after the timeout did not receive, then the receiver can take a proper action of handle that. Okay. And for non-blocking send, usually means the sender can resume execution as soon as the message is passed to the communication system. So to support non-blocking send, the communication system always requires some kind of buffer. Okay, so the message put into the buffer of the communication system, then the non-blocking send can be returned immediately. Now become the communication system's responsibility to guarantee the message will be delivered to the receiver. Okay, and for non-blocking receive, okay, the receiver can resume its execution immediately, but after this return, it may means two things. Okay, either a real message is returned, okay, or an error was sent to indicate that it returned without messages. Okay, depends on the desired message is already there or not. Okay, so non-blocking receive, you immediately get a return, but with a flag to indicate, okay, the return, the message buffer allocated really as a new message coming or it did not contain anything. Okay. Okay. So stop for take a break. Okay.
哦，还不行。
没有，我刚要换那个，要换一个账号。诶，哦，
你Google Meet 有开？
没有，因为我刚才知道要换学校账号。
啊，放什么？用学校账号？
对啊，用个人登不进去。
用那个其他的东西，其他东西。
还有我告诉你，
好，那个晚上的时候只会有，今天只会有1点钟。
对，他讲，
真的那时间，他跟我讲时间太晚了。我那时候就是因为我当天早上我才跟老师去。对啊，那另外一个业余的话，他也没有准备。
对啊，
业余张业余。所以我们没办法。
今天没有人报告。
有一个雨辰吗？
对。有一个。
他老师你那个下午都不会去啊？台积电那个郭宏伟啊，
在哪里？
管院520。
我再回去。
不会吧？那时候看一下时间哦，这时间好尴尬。因为那个硕一的都要上课。
哦，这样的。
对。
那时候排这个时间。
对啊，很奇怪啊，看到这个。
是睡眠堂课。
对，这么严啊。所以会少一些。
他为什么排这个时段？
到时候跟他讲一下，下次不要排这个时间，要不然会没有。而且重点是好像这届所有的都好找到工作。
哦，真的。
对，都不用去。
现在大家都缺人了。
缺啊，缺
到爆。这么缺，今年应该都很好找。
很好找吗？很好找。今年找工作很好找吗？
感觉也没有。
没有。然后再有2个礼拜又要考试。
好像是5月底的
第10周。
5月第1个礼拜要考。
这一周
还有下一周，再下一周。
这个没有开始准备题目。你这学什么课？
计算机架构。那个新老师那个就想要把它当做那个这个
就是张老师的。
对，张老师新老师。
他怎么样？
我觉得人还不错。重点不是考试难不难，是人还不错。
就是当然了，就是。
我这边要开荧幕分享。
对，要开，然后你那声音也要开。
然后没开掉。
因为我刚用个人账号登不进去。
别人登进来的吧？
是他的那个账号登不进去。就是他是用 Gmail 账号去登那个我们写的那个账号，然后就不行。所以他那个后面要那个左边第3个。
别人刚
应该是没有上线。
上来了。
对。不过他们应该都会比较倾向于直接看那影片吧。
所以要用什么账号？
要用学校的。学校的 Gmail 账号。
学校 Gmail 账号。
对，NYCU.edu 吗？不知道，忘记了。老师你会，然后那个你不是有叫我审一篇那个 personal information 吗？然后有想要听那个它里面到底要怎么做，还是我直接写报告给老师？
都可以啊，因为它里面有讲的够细的话，那把它讲一下也可以。
那我到时候再看看，因为我有看了一遍，大概有整理一些问题跟意见。
对啊，很好。我到时候，因为我们重点就是要看看人家在做类似的东西的时候，人家 应该是考量的是哪些东西嘛？对，我们有没有可以参考的点？对，不管它我们要将来怎么样，是另外一件事情。当然理论上我们不能够直接去参考它啊，但是我们可以记得就是如果有些问题我们都知道啊，那就是我们自己有没有考量那个东西？因为看人家的东西有时候就看到问题，自己在做的不见得看到问题。
确实
都是这样的。Okay, we're back. So conceptually, broken send plus broken receive, the behavior will be something like this. Okay, this is timeline. Okay, from pass to the color. Okay, so the sender will send message for broken send, and then it's execution with suspend. The message is delivered. Here we assume the receiver also execute this receive, and because it's broken receive, that means if message does not arrive, then the execution of receiver also be suspended until the message arrive. Then the receiver will be resume and eventually send back acknowledgement, okay, or response. Okay. And after get the acknowledgement or response, then the execution can resume. Okay. And here the acknowledgement depends on, okay, from these three different kind of implementation, then the acknowledgement may be generated by a different runtime. Okay. Here the host will generate acknowledgement. Here the process will generate acknowledgement. And here the acknowledgement will contain response also. Okay. So then, but we anyway it's an acknowledgement. Okay. So if instead of using broken send, we can use non-broken send. Okay. If the receiver is still broken receive, then the behavior of the sender will be something like after send, the execution can continue. Okay. And the receiver again can maybe suspended until the message arrive and eventually send out acknowledgement. And after the acknowledgement arrives to the sender side, then sender may be interrupted or signal by using signal handling to accept this notification, or sender may periodically poll its status about the messaging, and so on. Depends on the API supported by the communication system. Of course, a broken send can associate with a non-working receive. Then the sender will be suspended, but the receiver, because it is a non-working receive, so you always return immediately. So if the receiver is executed before the message arrives, then you will return immediately with null or error indication, indicate that there's no message received. And then the receiver side again interrupt or signal handling routine may be used, or receiver can pull its receiving buffer periodically. Eventually, when the message arrives, either way the receiver will have the knowledge, then it will accept this message and process, and eventually send out acknowledgement. And after acknowledgement arrives, sender can resume its execution. So something like that. So if both parties use non-broken semantic and then system, then you can see that both sender side and receiver side, they all need to have this asynchronous mechanism, interrupt or signal handling or periodical polling. We need to be used to address to this message status. The advantage and disadvantage of blocking primitive will be something like this. The blocking primitive is much easy to implement and understand, because the API is simple and the semantic is clear. So the use this primitive, the data flow control will be much easy for the application programmer. But of course, the disadvantage is that they may be blocked forever if the other party crash or message get lost or whatever. That's the problem for this. And also because it's broken, the concurrency degree between the sender and the receiver will be limited. Because it needs to be blocked there and cannot do other things. And also the last one is the communication deadlock can happen. Here is an example. For example, P1 and P2 process. And they both use this communication. P1 try to send a message to P2 and then waiting for acknowledgement or response. And P2 also do the same thing. Then it's possible if the blocking semantic are used, then both P1 and P2 they are blocked in this send. Then because this is a blocking. The message come here but nobody receives, because this process also blocked in send. And this we call it communication deadlock. It's possible to happen. So if the algorithm you used in this communication parties, P1 and P2, is something like this. Then this system always will block there. Because if P1 comes first, you block here, and then later P2 come here, you will also block there, and nobody can unblock this because they're both waiting for the other party to receive its message and to generate acknowledgement or response. For non-blocking operation, the advantage is that sender and receiver can continue their execution, so they don't need to wait each other. So there's no dependency between these two. Okay, they just continue doing their own work. Okay, but and also so it's unlikely they will run into deadlock. Okay, because they don't need to wait. Okay, so one of the major criteria for deadlock is you need to wait. Okay? You don't need to wait, then there's no deadlock can happen. Okay? The disadvantage is that it's difficult to know the message is really delivered, okay, or not. Okay, if this information is important, then you need to have a way to find out that. So you need to interrupt the signal handling or other mechanism we used to find out this. Okay, so that's the disadvantage. So you need to system need to support other facilities that these both parties to find out the real situation of the messaging. Okay, and also if the buffer management is an important issue, then sometimes the sender if the message is not delivered yet, then the buffer need to be locked there until the message is actually delivered. Then the sender can unlock the buffer. Okay, whatever. Okay. So to avoid this, sometimes we may need to have another data copy or other overhead to control information among these sender receivers, so they can find out the situation of this message. Okay. And or sometimes they need to copy the data to the buffer instead of lock the buffer. Okay. And so on. So that's the disadvantage or okay. But of course, it's a trade-off. Okay, depends on what kind of application you are implementing. So you can select a proper application API for your applications. Okay. So here, the major difference between this non-blocking and blocking primitive is buffer. Okay, if you allow buffer, you have system buffers to be used, can be used. Then non-blocking primitive become possible. Okay, if you don't have enough system buffer, then maybe sometimes you can only support the blocking semantics. Okay, so buffering become an important issue. Okay. So in general, a message need to be transferred from sender to receiver by coupling message, okay, from one address to another address. And this coupling can be directly copying, or you have an intermediate buffer in there. Okay, depends on what kind of implementation. Okay. So if a receiver is not ready to accept, then the communication system may need to set the message for later for the receiver to see. Okay. So the communication system may need to have buffer. Okay. So the buffering strategy will affect the implementation of this primitive. Specifically in blocking set, to support blocking set, we don't need to have any buffer in the sender's host. Okay. But if we like to support non-blocking set, then in sender's host, you always need to have some buffers there. Otherwise, it's impossible to support non-blocking set. And to support blocking receive, you can have buffer or without buffer in the receiver side. Okay. Of course, with buffer, it's much easier to implement. Okay. But without buffer, it's also possible. But you need to have a lot of control messages. Okay. Send generated. Okay. To support non-blocking receive, we also always need to have some buffer in receiver side. Okay. So And here we will discuss this situation with buffer and without buffer, okay, and how to implement this broken or not broken send. Okay. So here, to implement broken send, okay, with broken receive, okay, without any buffers, okay, and there in general you have two mechanisms. Okay. One we call send after receive. Okay, this policy that means a message only copy once from the sender's address to receiver's address directly, without any buffering mechanism in between. Okay. So message always in sender's process address space, and some control information will be exchanged to make sure that receiver is ready there, is ready to receive information. Only after this situation happens, then the message will be sent to the network and then eventually delivered to receiver side to receiver's address space. So it means a message is only copied once from the sender's address space to network and then to receiver's address space. Okay. Without any, of course, the network, the communication in the network part, the network may have go through a lot of store and forward buffer. We see that it's not the buffer in the host, okay, but the buffer in the network. Okay. Here the buffer means in the host. Okay. So for this kind of send after receive, that means when the receiver is ready, then the message will actually be sent. If the receiver is not ready, then the message is kept in sender's address space. Okay. So eventually the message is delivered to the receiver's address space and they may send out an egg. Okay. After that, okay, the message is delivered, okay, and so on. Okay. So before the message actually be delivered, you need to have a lot of control information or notification okay, without any message bodies. Okay, so maybe only have a header or whatever. You send from the sender, send a message to receiver, and receiver host after receive, you check if there's any receiver process broken there for this particular message or not. If not, then you will return not ready. Okay, and periodically the sender send this control information to the receiver host to make sure the receiving process is ready there. Okay, so that's why this is named send after receive. That means after receive become ready, then you actually send the real message. Before that, you only exchange the control information. Okay. So that's one. So, and the second strategy is that send, discard, and retry policy. That means the message may be copied several times. Okay. So when sender execute the send, okay, the sender wait for an egg, but the message is delivered to the sender, to the receiver side. If the receiver process is not ready, then the message is simply discard. Okay, and after timeout, the sender will resend. So that's it. Okay. Again, the message is kept in sender's address space. Okay, but whenever the network is ready, then you just send out and expect an egg comes back. If an egg comes back, that means receiver received. Okay. If there's no egg comes back after timeout, you just resend. Okay. So that's the name stands for send, discard, and retry. Discard means the receiver host find out there's no receive being processed waiting for this particular message, then just discard it. Okay. And then the sender's side anticipate a timeout, and then sender will resend again. So a message will actually copy multiple times, okay, to the receiver side, the host, receiver host. But only the last time the receiver actually receive, then they will generate an egg back. Other than that, the sender always get a timeout, and then we try, we send. Okay, so conceptually, it's something like here is the boundary of the nodes. Okay, so sender, the message is copied from the sender's address space to receiver's address space. Okay, without any physical any message buffer in this sender's host and receiver's host. Okay. The second part is we can use a single buffer, okay, for this broken send and broken receive. And this buffer can be put in the receiver host. Okay. If a receiver host use a single buffer, and then this broken send and broken receive will become much easy. Okay. So a message always copy twice. The first one is copy from the sender's process to receiver's buffer, system's buffer, and then second time it comes from receiver's buffer, host's buffer to receiving process. Okay, so with only a single buffer will be enough. Okay, so the sender will block until this receiver size buffer become ready. We don't need to wait until the receiving process is ready. As long as this system buffer is ready in the receiver's host, then the message can be delivered to this system buffer. The sender can get a return. Okay, and eventually, when the receiving process is ready, then the message will be delivered to the receiver process. Okay. But of course, we can have multiple buffer in receiver side. Okay. Then that means you allow multiple messages comes in to the same process. Okay, so the blocking time for sender will maybe minimized, maybe reduced in some sense. Okay? So it depends on, but one buffer sometimes is enough. Okay, so to support non-broken send with broken receive. Okay. One possibility is that we use multiple buffer strategy in sender's side, okay? Because remember we require sender to come non-blocking. That means whenever you try to send, you hope to get the return immediately. Okay, so that means if there's a buffer in sender's host, then as long as the buffer is available, the message is copied from the sender to this buffer, then the sender's primitive can return. Okay, so this is a non-broken send. Okay. Again, the message is always copied twice, one to the sender's host, and then copy to the receiver's address space. Okay. And here, instead of waiting in sender's process address space, the message is waiting in system's buffer. Okay. So, and this part. Okay, this part we can use these two strategies. Okay, two policies can be used for between the messages from this system buffer in the sender side to the receiving process. Either policy can be used. Okay, of course, if the receiving process we can use with a single buffer in the receiving process. Okay. You can have a single buffer in here. Okay. Then the blocking for the sender or the blocking for the receiver may be reduced. Okay, because if outstanding sender, the sender comes first and the message comes in, if the receiver is not ready, you can still put in the buffer waiting there, right? So, so it depends on how you put it together. Okay. So this is the simplest non-broken send with broken receive. Okay. With one or more buffer in sender side. This is 0 or more buffer in receiver side. Okay. But to support non-broken receive, we always need to have a buffer in the receiver side. Otherwise, it cannot tell the system it's non-broken. Okay. Otherwise, the receiving function must send confirmation to sender and wait for acknowledgement, okay, to determine you can return a message or not, right? So that violate the definition of non-blocking. Okay. So you always need to have a buffer to support non-blocking receive. Okay. So in general, a finite number of buffer can be used in receiver side to support non-blocking receive. So non-blocking receive can be associated with blocking set or non-blocking set. Okay. If you try to use non-blocking set, then the sender side they don't need to have a buffer. But if you require non-blocking set, then both sender and receiver can put a buffer there. Okay. So here, for non-blocking set, we need to have buffer. But for non-blocking receive, we also need buffer. Okay. So in general, to support this non-blocking set with non-blocking receive, then both sender side and receiver side can have multiple buffers. Okay, but depends on what kind of non-blocking granularity you try to support, okay? And then you can decide how many buffers you try to put in there. Okay, after discuss this buffering strategy, okay, so you can see that to implement this message passing facilities, you need to take care of buffer management, okay, in the host. Okay, most communication processes they use this client-server paradigm or computing model for the sender and receivers. Okay, and because most communicating processes, okay, they have these communication parties in general, their roles may be a little bit different. Okay, in most cases, their roles are asymmetric because a process we call servo usually is a process that provides some services, and it is passively waiting there, waiting for incoming request message. Whenever there's an incoming request, then after receive the incoming request, it do some action to handle this request. Okay, so it's a request dependent, depends on the content of the request message. Then the server will perform some proper action, okay, for that particular request, and then generate response. Okay. So this kind of process we call it servo process. Okay, it's a passive role in the communication. Okay. And the other process which we call client, usually they generate request first. So the client usually is the party which actively generate or initialize the communication between the processes. Okay, because the client process usually means it has some needs from the server. Okay, so you need to tell the server what is your need. So you generate a request to the server, and then server after receive the request message contain the requirement of the client, then server can perform some proper action to handle that, to generate response, and so on. Okay, so the communication parties usually have these two different roles, a client and servers. Okay, so their roles are asymmetric. Okay, many well-known internet services they are this kind of applications. Okay, so any internet server and your client, a terminal client, their role are among these client and servers. Okay, your client application is in your terminal, in your PC, in your mobile phone. Okay, And the server process is run in data centers and whatever. Okay. The original, they will not initiate communication. Okay. Communication always initiated by the client process. Okay. So most distributed systems, they use this client server paradigm as their communication models. And in client server model paradigms, we need to handle, because the message close the network, there are no boundaries, and in the network, goes through the network. So some failure due to happen, okay? And basically, you have this three kind of common errors can happen, okay? Or failures can happen. The message can lost, request can lost, and the response maybe get lost. That's why the server may crash, okay? So, and to handle this exception, we need to have a reliable message passing system. Okay, the message passing system or underlying communication should be able to support this, so the application did not need to handle that. Okay. Here we will see that this is a scenario: unsuccessful request execution. Okay, here this one is request lost, so message just drop out in before arrive receive, and response lost. It means the server get the message and process, but the response did not come back to the client safely, successfully. It got lost. Okay, during the reply the message, and the last case is that server somehow crashed after receive the message. Okay, so there's no response generated. Okay. There are some handshaking protocol commonly used to handle these three kind of common errors or failures. Okay. The first one we call request acknowledgement, response acknowledgement, or RARA protocol. Okay. The acknowledgement and timeout and retransmission are used to support this one. So the handshaking is something like client send a request and server after receive request first send out an acknowledgement, and then process the request, eventually generate reply. Client after receive the reply also generate an acknowledgement back to the server. So, okay. And here this means the both server and client they may need to block in these two places, okay, waiting for acknowledgement. Okay. And this protocol can be used to handle these three kind of failures. Okay. This egg serve to make sure that client the message is received by server safely. So without this acknowledgement comes back in a time quantum predefined time quantum, then the client will resend the request. So retransmission is always used according to the timeout. Okay. So after timeout, the acknowledgement did not come back, then retransmission will be played. And here again, after this reply sent out, the server also set timer. If the acknowledgement comes back before the time expires, then it's alright. Otherwise, it will resend the reply. Okay. After timeout and so on. Okay. So both server and client they use acknowledgement with timeout and plus retransmission, okay, to make sure that this request has and response are all well acknowledged. Okay. But because here you can see that these two messages, acknowledgement and reply, are both sent from the server to the client, right? So actually this one of them is become redundant, especially this one, the first acknowledgement. When reply comes back to the client, it means that server received the request safely. Okay, so this acknowledgement can be eliminated. The only problem is that the timeout set for client now not only need to cope with the round trip delay, they all need to contain or cope with this processing delay of the server for a particular request. Okay, so as long as the timer set enough properly, then this acknowledgement can be eliminated. Okay, so we have this new protocol called request response with egg, or sometimes called RRA protocol. So the first acknowledgement can be eliminated. So as long as we set a longer timeout. But because the execution time for the server sometimes may be unexpected, okay. So the server can have an option. Okay. So when it receives a request, you start an internal timer. If after this internal timer expires, the reply is not generated, then the server will send out an egg back first to inform the client that the request is received. But however, because this particular request need a lot of time to process, so cannot generate reply yet. But this client did not need to resend the request first. Okay, so this option egg can be added when it is needed. So if the server anticipates some long execution time, okay, then it can send out an egg before the reply. Okay. And again, of course, they both need to have a timer. Okay. So only the last egg, okay, will be needed. Okay. So RRA means that. Okay. Then eventually, this last egg can be eliminated also, because most communication for client and a particular server, the handshake usually or the request reply usually is not happen once. Okay. When the relationship between the client and the server generated or built, usually the client may generate after receive this response. You may generate a new message for the next request or whatever. Okay. So if there's a new request that comes in, follow this reply, then this egg can be eliminated also for the response egg. Okay. That's why eventually we will have this reduced protocol or request response protocol. So the egg from the server, Okay. This egg from the client to the server. Okay, not the last one. Okay, from client to the server in RA may be not necessary. Okay. Because if this client did not receive this reply during its timeout, during the time expire, then the client will resend the request, right? So without this egg, if receiver receive the duplicated request, then server would know, okay, its reply get lost. Okay. So if response lost, client will resend the request after timeout, and server they can just return the response to the client. Okay, they may process the request again, okay, and return, or without process the request. Depends on how the server handle this duplicate message. Okay, so both client and server, their egg can be eliminated. Okay, in this particular case. Okay. So here we change this to from client to server. The last egg, that egg, okay, can be, because without this, if the server receive a retransmission request, then server will know the reply is get lost. Okay. So here, this RR protocol usually ensure that the request is executed at least once. Okay. Means the server may receive a multiple requests. Okay. And this is a special scenario. Okay. For example, here you can see that the sender, the first request get lost, so eventually you will be transmission. If this transmission comes in but server crash before generate response, then another timeout will happen in sender side, and then eventually sender will retransmit the request again. If this retransmission here, several retransmission may happen, but eventually there's a one retransmission request comes in, and server is already recovered and successfully execute this request and generate response. If this response get lost, eventually this client will come out again. Then they will transmit request. Okay. If this request also successfully received, okay, then server may execute it again, generate second request, second response. Okay. And if that's one, this response is safely arrived, then there's no retransmission will generate. Okay. So you can see that. Okay. If multiple requests may be executed by the server, but only the last response will take action, will be effective. Okay. The other request will become irrelevant. Okay. So sometimes this at least once we semantic also call last one semantic. That means the last execution or last response is the effective one. Okay. The other previous response, because due to any reasons, it is not received by the sender, so they become irrelevant. Okay. And this RR protocol makes sure that request will be executed at least once by the server. Okay. There may be multiple times, but only the last time, last one, become effective. Okay. So these two names, okay, usually means the same thing. Okay. If you see at this once, it actually means that's one. Okay. Some service function can be executed multiple times without any side effect. We mentioned that before. And this kind of operation we call attempted operation. And attemptancy usually means repeatability. Okay, and an operation is attempted means you can generate same result without any side effect. Okay. So at least one semantic is only proper for identity service, because any multiple execution without side effect, so on last one become effective is alright. Okay. But some service is not non-identical, then this at least once or last one semantic will become non-proper. Okay, it's not. Then we need to have exactly one semantics. Okay. To support this, by using RR protocol, then we need to have sequence number or unique ID for the request, and also server need to have a storage to record the response for each request. Okay. Something like here. Server need to maintain a record for each request and its corresponding response. Okay. Here is for example, request, and the server first need to check this ID. Say request 1 is the first request, so it will execute the response, the general response, and set the reply. So reply is successful, okay, and send back. If the response get lost, then the transmission will happen. When server receive a message by using this ID, request ID, you will check, okay, this is a duplicated request. So the server will not execute the response. They just copy this response directly from this cached record, okay, and return this result again. So RR protocol with this sequence ID in the center and cache in the server side, then it can support exactly once semantic guarantee that the only one execution will be take place in the server side. Before now, the communication we are talking about for one-to-one communication. That means the sender with a particular receiver, okay, and the communication happen only between these two entities. Okay, but some application they may require a message be delivered or the messaging is among a set of processes instead of two processes. This we call group communication. Group communication happens in multiple parties, okay, based on a notion of groups. A group usually means a set of parties or entity process. They want to exchange information in a reliable and consistent manner. Okay? Not only reliable, but also need to be consistent. Okay? Reliable means the message can be delivered to all anticipated parties. Consistent means everybody receive the message in the same consistent way. Okay? So there are basically three types of group communication. It's one-to-many, so single sender with multiple receivers. Okay? Sometimes we call it multicasting for this kind of communication. Second one is many-to-one. That means you may have multiple senders with only one receiver. It's not a client server, okay? It means that the receiver, the message generated by those set of multiple senders, only one message may be, sometimes it may be the first one comes to the receiver and the receiver will continue its operation. And the later arrived message will maybe just discarded by the receiver.